can consider. And the 10th principle, last one, is to consider all weather situations. So we may design our system, for example, to treat up to a 3-month event, but we really need to know how it's going to behave in periods of greater and less rainfall than that. And so if we think about this sort of simple kind of classification system proposed here, so in dry weather, Frederick and I believe that it's really important to think about how will vegetation be sustained, what will the system look like. A system that starts to look terrible or plants die during dry weather is not going to be sustainable in the long term. And again, we might need to think about monitoring systems that alert us to that risk. Fairly easy with soil moisture that's connected to telemetry and tells us. In our wet weather, up to say a 10-year average recurrence interval system, we need to control the flow into the system, control the pollution, etc. We may have a bypass even there. And then for really large events, we need to make sure that the system does not compromise the hydraulic capacity of the drainage system. So water sensitive urban design is not about foregoing drainage performance in order to get flow regime and water quality outcomes. We need to make sure that our conveyance system is still able to work appropriately, and so we can convey those above design flows safely. Let's talk a little bit about that flow regime or stormwater quantity management. We've already talked about this a little bit before. We know that urbanisation typically reduces our base flows, and not always, because we can get other things like leaking water supply, wastewater that increases it. But because it decreases infiltration, broadly speaking, it decreases our base flows, and absolutely and ubiquitously, it increases our peaks. And that has really big impacts, as we've talked about. Our colleague Perrine Hamel developed this conceptual diagram that suggests that we need to put together a landscape that deals with both of these. So we need systems that infiltrate some water. We need systems that capture, such as those rainwater tanks, capture water. We need perhaps using some of that for irrigation to recharge that groundwater and therefore those base flows. So we should be, in a way, thinking about those two little charts on the left and thinking, okay, what is this landscape? What do I have to engineer into this landscape to reverse that? What are the various components I'm going to put together to allow that to work? And so rainwater harvesting on site, at individual house scale or at a large scale. Here we see a system where you've got an automatic changeover between the tank water and the mains water, so that if the tank runs out of water, we automatically switch over. What's really important is that if we're going to use rainwater harvesting, we need to go looking for uses that are going to place regular demands on that water. In other words, draw down that tank regularly. If we just use it for garden then for much of the year we won't use any. And in fact, we won't use any if people aren't interested in the garden. So we need to lock in some more regular uses, such as toilet flushing, such as hot water if we can, or laundry if we can, depending on local regulations, and depending on appropriate treatment facilities. In this case here, we see a treatment system in place, so a UV treatment system in place, so that we've got high quality treated water. We're also seeing now the very ready availability of sophisticated real-time control systems, even for small scale like this. In Australia, there's a system called Tank Talk, developed by one of the water authorities, Southeast Water, that allows that tank system to be connected to the weather forecasts and to provide a controlled release of water before a storm, so that tank won't then overflow into the drainage network during the storm. those systems are being enhanced to even release that water in a form over a longer period to provide base flows. So this advent of really nice control technologies and sensor technologies is allowing us to do things we wouldn't have even imagined even 5-10 years ago. We want to, if we go back to Perrine's nice concept diagram, we want to not just capture those peaks, but put some water back into the base flow. And we can do that with infiltration, but at the same time also promoting evapotranspiration to reduce the overall runoff volume, because that will also have benefits in terms of urban cooling because we're promoting shade because we're promoting vegetation. Here's some examples of stormwater harvesting from a project that our team's been running, the little Stringybark Creek project to the east of Melbourne. These are on the top left a household scale system, and then a system applied at a school, a much larger system at a school. Or we could use big underground storages so that we don't lose the use of that space, and that could then become a park. Or infiltration using a whole range of sort of systems, really natural looking kind of systems such as these swales, etc., to allow us to just have a nice looking landscape, but to get some of that water back into the landscape. Or, these kind of simple systems here. Or a little rain garden at the individual household scale. This is a system that colleagues and I built as a demonstration in someone's property, and they really like it as a sort of an element of their garden, and all of their stormwater runoff after their rainwater tanks goes into that system, sustains the plants, which as you can see are very healthy, but also allows that water to recharge groundwater.